Good evening, good morning, and good afternoon to all of you. Professor Anirban Datta from University at Buffalo, Sunny, and myself, Professor Uttama Lahiri from Indian Institute of Technology, Gandhinagar, are jointly organizing a webinar series on translation and research in neuroengineering and neurorehabilitation. In this, we will be focusing on emerging applications of neuroengineering while covering topics in engineering perspectives to neuromodulation, cost-effective technologies used in neurorehabilitation, and the clinician's perspective to neuroengineering. The speaker for today is Dr. Suvranu De. He would be speaking on non-invasive brain imaging for bimanual surgical skill assessment. This is his talk title. Let me quickly introduce him before he starts, introduce him to the participants. So Dr. Suvranu De is the Erik Jonsson 22 Distinguished Professor of Engineering at Rensselaer Polytechnic Institute, where he serves as head of the Department of Mechanical, Aerospace, and Nuclear Engineering, and director of the Center for Modeling, Simulation, and Imaging in Medicine. He received his Sc.D in mechanical engineering from MIT in 2001. He is senior member of IEEE and serves as vice chair for the award section of the IEEE Technical Committee on Haptics and leads and also co-leads several committees of the Society of American Gastrointestinal and Endoscopic Surgeons. He is an elected fellow of 3 professional societies: the American Institute for Medical and Biological Engineering, the International Association for Computational Mechanics, and the United States Association for Computational Mechanics. Dr. De, really very nice to have you as the speaker for today's webinar. Now the floor is yours. Please go ahead.
Thank you very much, Professor Lahiri, for this very, very kind introduction. I'd like to share my screen. So I think you'll have to, yeah, thank you. All right. So again, good afternoon, good morning, good evening to all of you who are listening. Thank you so much for being here. I'm really, really pleased, honored to be invited. And I hope that all of you are doing well in this unprecedented times. So I have no disclosures. For those of you who have not heard what our RPI or Rensselaer Polytechnic Institute is, I'm just going to give you a brief introduction. So I just looked at Google and it's about 7,398 miles from IIT Gandhinagar, and right about here on the border of New York State and Massachusetts. So established in 1824, RPI is America's first technological research university. And it was founded by 2 unconventional duo of Stephen Van Rensselaer, who was a politician, a militia officer, and a businessman, who was educated at Harvard, and Amos Eden, a botanist, a geologist, and an educator who was trained in Williams College. So Eden is one of the pioneers of what we know very well now as the experiential learning model. So at that time, when liberal arts education permeated the Western world, Amos Eden was one of the very first few people who were talking about experiential learning, going out in the field, collecting data, you know, talking about research to each other and so on and so forth. So this threatened that liberal arts establishment so much so that different universities started setting up schools of engineering and science. So my department, Mechanical, Aerospace, and Nuclear Engineering, which we may call MAIN for short, is the largest department at Rensselaer. And we have about 50 faculty members and 1,440 undergraduate students, 250 graduate students. I also wear another hat, as Professor Lahiri pointed out. I serve as the director for an institute-wide research center known as the Center for Modeling, Simulation, and Imaging in Medicine. And the goal of the center is to actively develop advanced modeling, simulation, and imaging technology for healthcare through interdisciplinary collaborations with the aim of transitioning the technology to clinical practice. So we have 4 major thrust areas of virtual surgery, non-invasive brain imaging and neuromodulation, computational imaging, tissue manufacturing, characterization, and diagnosis. So we work in this center. I co-direct the center with Professor Xavier Intes, and you are going to hear a lot of references to Professor Intes' work because we worked very closely together, and he's from the Department of Biomedical Engineering. So we collaborated with about 20 faculty members from 4 different schools on campus, the schools of engineering, science, humanities and social sciences, and architecture. But there's a bit of a problem because we are a translational clinical center in a technological research university with no medical center. So we collaborate widely with a large number of clinical centers in the country, a few of them in the state of New York, including the University at Buffalo, where Dr. Datta is from, and Albany Medical Center, Mount Sinai, and a bunch of medical centers in the state of Massachusetts, particularly those associated with the Harvard Medical School system, and then in the state of Texas and Indiana. Internationally, we work with the University of Western Australia and the University of Strasbourg for medical robotics. So today I'm going to be talking about surgery, and though the topic of my presentation is about neuroimaging for bimanual surgical motor skills, as was pointed out earlier, I'll start with a much broader vision of what we're trying to do in the center and how that is very unique and how neuroimaging fits into that framework. So surgery is one of the most complex tasks that human beings are called upon to perform. It requires mastery of fine motor skills, superb cognitive skills, and the ability to work effectively in a team. Surgery is not only a complex task, but is also performed in an extremely complex environment of the operating room, full of distractions, interruptions, time pressures, and emergencies. So whenever you're performing a complex task in a very complex environment, you can be sure of one thing, and that is error. So this 2000 report from the Institute of Medicine in the US shocked the nation by proclaiming that about 98,000 Americans die per year of medical errors. So let's pause and think about that for a second. That's about a Boeing 747 with 270 passengers going down every single day. Unfortunately, the estimates then were actually much lower than what the actual numbers are. And according to the Centers for Disease Control, who we see on television almost every day, the toll is much higher, and medical errors are actually the 3rd leading cause of death in this country, right after heart disease and cancer. So this is indeed a quite crisis. So even with the best of intentions, errors occur in surgery and mostly during the learning phase of a surgeon. So since the time of Sushruta in 600 BC India, surgeons have been trained in the operating room on human patients. So the modern residency program, which was put in place by William Halsted in the early part of the last century, has its fundamental principle that surgeons must be trained in the operating room. So this places undue risk on the human patients. So a resident may encounter just a handful, if at all, of rare critical cases before she graduates. Individualized attention is costly. There's hardly any way to objectively assess performance, and we're going to be talking about that quite a bit later on, and the progress of the trainee through the system. So the training is not really adaptive, that there's no structured way to lead from one level of complexity to another. So those of you who play video games know exactly what I'm talking about. So exactly, this is a much higher stakes than video games. And the focus is mostly on procedural skills. The residency program is further challenged by reduction to 80-hour work week in the United States, increase in malpractice liability, and reduced hospital stays, which have all reduced the contact hours with patients. With all these problems, the question that we have started asking in our center and in the larger medical or society in general is that, can we rethink the model of surgical training and certification? Of course, the best part of training is the personalized education overseen by experts. So can we then deconstruct this model? So what is exactly happening during the learning process? So as the learners work on a surgical process, their actions are being observed by a seasoned expert. The expert has a mental model of what the correct action should be. He or she compares the observed actions with that mental model and then provides feedback based upon that observation. I'm oversimplifying, of course, right? But this is a very general approach of personalized one-to-one training. And once the performance exceeds expert level performance, of course, the trainee is eligible for certification. So how are these budding surgeons, those trainees that we're talking about, assessed? In the vast majority of the cases, they're assessed using what I call these checklists. Things like objective structured assessment of technical skills, OSATs, or goals, or GRITs. They're basically checklists where the attending surgeon is observing a young junior surgeon and then sort of checking things off on the list. There are so-called, so these global rating scales have a lot of well-known problems. They have inconsistent inter-rater reliability, they have subjective metrics, halo effects, and poor correlations with patient outcomes. There are also these more quote-unquote objective metrics of task performance, which are mostly a combination of task completion time and performance errors. These also have well-known errors, for example, because think about it. The quality of task performance or the quality of surgery is not guaranteed to be linked with how fast the surgical process is completed, right? And there's no consensus on what error measures should be measured and how that correlates to outcome of the surgical process. I'm going to be talking about the FLS, the fundamentals of laparoscopic surgery, in a bit. So in this talk, I'll focus on what is known as laparoscopic surgery. So in this technique, long, slender tools are inserted into the body of the patient. So as you can see in this, I hope you can see my pointer. So they're inserted into the body of the patient, and the internal organs are visualized using a wide-angle camera. So that's called the laparoscope. So if you see here, there's a wide-angle camera which is connected to the monitor. So essentially, the surgeons are looking at a video monitor here while performing surgery. It's kind of like playing a video game anyways. So this kind of surgery has many advantages: a minimal incision, reduced pain, shorter recovery time. But this technique relies on very complex bimanual motor skills and hand-eye coordination. Think about it. Because these tools are pivoted at the stroke arcs at the points of entry, so if you move to the left, the tip of the tool is going to move to the right because of the pivoting. And your brain has to get adjusted to that motion. Because there is no longer direct contact with the organs, there's very poor tactile perception. And since the entire visualization field is really two-dimensional, there's poor depth perception. And there's limited field of view, which is limited by the field of view of the camera. So now that you understand the limitations of current training and certification methods, so how can technology help? As we all know, technological progress is on a steep upward climb. Since the first industrial revolution, which happened in the late 1700s with the steam engine, things have been happening in rapid progression. Next came electricity, followed by the computer and digitization. We are currently in the fourth industrial revolution, according to some, ushered in by an unprecedented convergence in technologies. So if you look around, we are most definitely in the age of AI, whatever that means. To us, it actually means collecting lots and lots of data and being able to make sense of the data and use that for a purpose. So what does surgical training and certification mean in this age of AI? So instead of observing a single trainee, can we create a model of trainees based upon lots and lots of data? So what kind of data are we talking about? All kinds of data. kinematic data of motion, force interactions, eye motions, physiological data such as galvanic skin conductance, blood pressure, heart rate, brain activity included. And yes, that's where neuroimaging comes in. So what we can build is what is called the learner model. So this is an intelligent agent that represents the trainee population. We can build this very similar model for experts. So rather than depending upon the mental model of a single expert, we can have the collective intelligence and expertise of many experts. So when now we are observing, so these are two agents we can actually build based upon lots and lots of data. Now, when we're observing a single trainee, we can use that learner model to predict the possible actions, the next steps based on the current state. And we can then use the cognitive model to predict the correct actions based on the current state of the trainee. All right. So with the predicted actions and the correct actions, if they match, wonderful, you have a green light, things are going fine. If not, there's a virtual preceptor model, the third intelligent agent that looks at the two and selects the feedback based upon action mismatch. Right? So that goes to the trainee. Now, if the performance of the learner exceeds expert level performance consistently, he or she is eligible for certification. So there's a lot of advantages to this model, which we call the virtual intelligent preceptor, or the VIP, that is being funded by the National Institutes of Health. And we've been able to demonstrate its effectiveness in multicentral study with more than 230 clinicians, and the study is being written up right now. There's already a couple of publications on that, but a very large study has been done, and that is being written up and published as we speak. So to put things in perspective, the research in this direction actually is at the intersection of artificial intelligence, where we are building all these cognitive agents, neuroimaging, where we can actually figure out what's going on in the human brain while that person is learning, and that data can be used with other data, as we just discussed, and then virtual reality. So why virtual reality? Because now we can actually create scenarios pretty much with a flick of a button, right? With a level of complexity based on the current level of competence of the trainee. So no longer is that whole resonating program going to be unstructured. It's going to be very structured and adaptive. So adaptive education is a dream. And this is something that we are trying to build ground up. So of course, I won't have time to talk about all three of them. I'll briefly touch upon virtual reality because that's so much a part and parcel of what we do. And that links directly to the neuroimaging part. So pardon me for digressing a little bit. Hopefully it's not too much of a digression. But virtual reality to us, as I said, is really the sandbox in which we can generate very complex scenarios that do not even belong to the earth. We can create any scenario we want with very high fidelity. It's a risk-free environment. It's a super reality environment where an individual can interact with the human anatomy using his or her senses of vision, as well as touch and other senses using interface devices. And now I can actually create rare conditions with literally a flick of a button. And I can come up with measures of evaluation at a much finer grained level than I could ever think of in real life. So we have put some of these thoughts in this paper that was published a few years ago. So you might think that, well, if this is all about generating scenarios, you might use software packages like the finite element methods that are used in the car and automobile industry, or you can just pay the folks in Hollywood a bunch of money and they would generate very nice graphics for you, right? But unfortunately, that's not as simple, because generating high quality virtual environments, the kind of things that we're talking about, is one of the 14 grand challenges that was put out in 2009 or about that time by the National Academy of Engineering in the United States. And if you look deeper into that statement, they're talking about very similar things that we work on. And the reason that this is a grand challenge is because we have to satisfy real-time interactions with high fidelity interactions. I'm not going to go deeper into that, but a lot of the work that we do in the center is focused on solving differential equations or integral equations at extraordinarily high speeds. So I'm going to show you one of our VR simulation systems. And this is Jamie Adair, for example, at BIDMC, Beth Israel Deaconess Medical Center in Boston. So this is a mannequin with actual surgical tools inserted in it through trocars, and they're linked to robotic devices. Jamie is also operating foot pedal to activate electrosurgical tool. So this is actually a virtual environment that he's interacting with, developed by us. The whole entire system is developed by us from our center. It was about 10 years ago. So these surgical tools actually interact with are connected to a robotic device, and Jamie's hand motions are being converted to the motions of the tool in the virtual environment using the robotic devices. Now, as you can see here, so this is the stomach right here. This is the liver, this is the pars flaccida, these are surgical tools, and he's trying to burn a hole in the pars flaccida so that he can pass a gastric band around the stomach. All these computations are being done in real time by solving partial differential equations. And as you see, the organs deform, and as the virtual tools interact with the organs, the interaction forces are being fed back to the user to the same interfaces, the haptic interfaces. So this is what we call the first generation of Gen 1 surgical simulation system, which is great for one-to-one interactions, captures the complexity of the tasks, and primarily used for procedural skills. Excuse me. But I also talked to you about cognitive loads that are in the surgical suite. So we captured that in a system called the Gen 2, or the next generation, where we actually can immerse the surgeon in a virtual operating room operating on a virtual patient. So this is, think of this as two recursions of virtual reality. So the reason we do it is now we can actually present interruptions and distractions in a controlled manner and measure the performance as a function of those. So we have performed many studies. I'll go quickly over. One of the studies was performed with 3 groups, a control group, a group that was trained on virtual reality, and the other one, a virtual reality trainer with cognitive load. So both these simulation groups were trained about 100 times with the repeated training on these VR systems with no distractions to allow them to reach automaticity. But after that, the VR plus CL group had 50 trials with cognitive load, whereas the VR group had none of that. So they just went 50 more trials without any cognitive load. So as you can see here in the post-test, after the completion of the study, both the VR and the VR plus CL group have almost identical performance. There's no statistical difference between the performance of the 2 groups. And that also shows out in the retention study performed a couple of weeks later. So that means they have reached automaticity. They can perform the task almost without thinking. But now they're asked to perform a clinical relevant task, which we call the transfer task. I'm going to talk about transfer task quite a bit. When they're asked to perform this transfer task with cognitive load, the group that was trained with cognitive load performs better, as expected. And this has been published. This is actually accepted and is available online in the American Journal of Surgery. And this study was performed in Baylor University Medical Center with Texas A&M medical students. So the past 15 years or so, we've been performing quite a few projects with funding from the National Institute of Science, National Institute of Health in the United States. And of course, there are many and varied, as you can see, ranging from surgery to endoscopy. I would not have time to cover or talk about any of them. And if you're interested on generating some of these scenarios or scenes or simulation systems, we have what is called the Interactive Medical Simulation Toolkit, or IMSTK. This is a freely available open source software that can be downloaded from this website. And this we have developed in collaboration with a company called Kitware, which is very well known for their systems like the VTK, ITK, Slicer, and so on. Highly modular, cross-platform, and real-time performance of surgical procedures. So I'll talk about a virtual FLS. The fundamentals of laparoscopic surgery was a system that was developed in the United States in about 20 years ago, and then by a joint group, a committee of the Society for American Gastrointestinal Endoscopic Surgeons, and the American College of Surgeons. And in 2009, this is the first system that was required for board certification in general surgery. So believe it or not, most surgical board exams did not require any kind of technical testing before certification. So general surgery was the first to require the fundamentals of laparoscopic surgery as a test before sitting for the board exams. And very recently, last year, the OB-GYN group also decided to include this as part of the board certification. So what it does include is, there's two parts. One is a cognitive test. The other is a psychomotor test of being able to perform 5 tasks. So the tasks are peg transfer, transferring pegs on a board, cutting a pattern like a circle on a gauze, ligating a loop, and suturing with both intracorporeal and extracorporeal knot time. So that is the current fundamentals of laparoscopic surgery. And as I said, this is required for board certification. So one of the projects that we had is to develop an entire virtual version of the fundamentals of laparoscopic surgery task. So this is on your left-hand side here, you can see the FLS, the actual physical simulator box where you can perform the tasks and you'll be observed. The scoring system is actually based upon the time and error, and that requires some time. Actually, a proctor is going to be observing you for the time, and then the errors are computed later, and then you're going to get a score. And this is a pass or fail score that you're going to get later, right? Not right then and there. It is quite intensive in terms of the engagement of personnel as well as resources, because you have to actually ship a $3,000 box somewhere, both within the US and outside, because a large number of countries do use the fundamentals of laparoscopic surgery. So to mitigate all these issues, we actually developed the virtual FLS, which we call the Virtual Basic Laparoscopic Skill Trainer, or the VBLAST. As I said, is purely virtual. And for example, this is a peg transfer task in the virtual reality scenario. You can not only do the task, but also feel the forces. And this is the pattern cutting task, which I'm going to be talking about quite a bit. This requires cutting a pattern. So as you can see here, you're using virtual tools to cut a virtual gauze. So, and as you cut around the circle, so the error is the error that you have made in cutting this circular, the circle that is painted on the gauze, right? And the advantage of the system is that it uses the same formula for computing the FLS scores, but that is built into the system. Therefore, you can get the scores in real time. And then, of course, we have done it for others. So this project is in collaboration with Professor Daniel Jones from Harvard Med School and Professor Steven Schweitzberg, who was also at Harvard Med School, but moved to the University at Buffalo. Right now, the former, he's the chair of surgery at University of Buffalo. And he's the former chair of the FLS committee. And I too serve on that committee. And we are in the process of developing and coming up with a newer version of the fundamentals of laparoscopic surgery. So as I mentioned, it has both a hardware and a software interface. And that's important because you not only see the visuals, but you can also feel the forces, and it is automatic. But how do you know it is any good, right? Because it could just well be a video game. And it is not, frankly, because we have done many studies that have been published on this specific system. And I'm just going to quote one of the studies here that was performed at the University at Buffalo. And this is called the Learning Curve Study, Learning Curve Retention and Transfer Study, where 18 students at University of Buffalo were randomized in 3 groups: the FLS, the virtual FLS, or the VBLAST, and control. The control group had no training. The training groups performed at most 10 trials a day. So they're performing these trials every day for 12 consecutive days. And as you can see, their performance goes up, becomes better, and then plateaus, as it should. Then they wait for 2 weeks. And they perform 3 FLS and 3 VBLAST tasks, which is known as the retention tasks, right? So as you can see here, the performance has degraded a bit, but what you can see is that at the start, There's no significant difference between the training groups and the control, but at the post-test, both the FLS trained and the VBLAST trained groups significantly outperformed the untrained group. And there is, so this has been published in Surgical Endoscopy in 2018. Now we come to non-invasive brain imaging as a tool for assessment. So I put that in perspective because we are looking at this as one of our measures so that we can build the cognitive model and the expert model, going back to the VIP model that I talked about. So functional near-infrared spectroscopy is the technique of choice. I'm sure you are familiar with those. The technology, I'm not going to talk about it much, but is non-invasive, and brain activation leads to hemodynamic changes, which is actually measured. Advantages are that, of course, is non-obtrusive, so people can wear that and move around. There's also a wireless version of this. It's real time, much less expensive than fMRI, and it has a moderate depth of penetration. So we use a commercial system from TechN, and we have also used commercial systems from NearX. It's a continuous wave infrared spectrometer. And for all the software parts of this project, we have collaborated very closely with Dr. David Boa's group, who moved from Mass General Hospital to Boston University, and Mariam Yusel, both at Boston University right now. So we chose to look at 3 regions of the brain. I believe we're the first group to look at all 3 regions of the brain for the FLS tasks. The prefrontal cortex, the supplementary motor area, and the primary motor cortex using FNES. The PFC is directly involved with other cortical lobes, such as the temporal or parietal, due to its role in high order cognitive functions, such as intellectual judgment and predicative functions. The primary cortex is located anterior to the central sulcus and is the seat of voluntary control of the motor movements. And located on the medial surface of the premotor cortex, the supplementary motor area is another region that is heavily involved in voluntary motion, voluntary control of motions. So the proof configuration is shown here, and we use short separation fibers to take out, to regress out the drifts. So what are the questions that we're asking using FNES? The first and foremost in our mind, of course, is surgical certification. So we discussed about the subjective nature of the current techniques of surgical certification, and we want to make it more objective. To be able to do that, we're asking 2 questions. Can we discriminate between experts and novices reliably using FNES? And how does it compare with the gold standard, which is the FLS course? Excuse me. The second question we're asking is, can we measure skill learning and transfer to the clinic or to a clinical scenario? Again, the sub-questions are, does FNES reflect surgical skill acquisition? Can we discriminate between skilled and unskilled trainees, meaning the trainees that have just started to learn and the ones that are more advanced, or some of the trainees may not reach proficiency? Third question is, can we detect skill transfer in an unfamiliar environment? Because surgeons learn on the simulators, but have to actually perform on human patients, right? So there are 2 kinds of transfers. One is near transfer, there's far transfer. For example, you learn to drive a Toyota. Can you drive a Ford? Maybe. But can you also fly a plane, right? That's very different. The third question we're going to ask is, can we predict the FLS scores? The FLS scores is still the gold standard. So there is advantage to be able to predict those scores, but directly from brain imaging. So can FNES predict accurately the FLS scores for bedside feedback? And how well does machine learning or deep learning techniques perform with these small data sets? Because I'm going to talk about unabashedly about the need for much more data and the need for societal interactions to create large-scale databases if we are to succeed in this kind of research. So I'll first start with the surgical skill certification. So to address the first question, that is, a neuroimaging method can discriminate between established skill levels, we recruited 8 expert surgeons who we defined by folks with either in the PGY or postgraduate years 4 to 5, or attending surgeons who have performed an average about 700 laparoscopic surgeries already. And nine novice subjects who we defined as PGY 1 to 3, postgraduate years 1 to 3, with an average of 60 laparoscopic procedures already performed. So there's quite a big gap in their procedural experience. So these subjects were recruited at Massachusetts General Hospital, which is a teaching hospital of the Harvard Medical School system. And we worked very closely with Dr. Denise G at that hospital. Each group performed the FLS pattern cutting task 5 times with a rest period of 1 minute between the tasks. We obtained the raw FNES signals and also compute the FLS scores. So let me point out, this is the first study to acquire FLS performance scores simultaneously with neuroimaging data. What we observed is the novice surgeons have significantly higher functional activation in the PFC region, as you can see here, and significantly lower functional activation in the left medial M1 and right lateral M1 and the SMA compared to expert surgeons. So one thing to note is habituation, which is the phenomena where response to stimulus gradually reduces due to repetition, was not observed in the study. Perhaps because the duration of the task was short. So remember that when we're talking about certification, the first question we ask is, can we discriminate between experts and novice? And the answer was yes. So now, how does FNES compare to FLS scores? So this was the second question we asked. Dr. Larry, let me know if we should stop and answer questions. I'm happy to do that because I see two individuals raise hands.
I think so. You can carry on, and maybe towards the end we can go ahead.
Absolutely. So those of you who are willing to to ask questions, please go ahead and post the questions. I'm happy to answer. So as we were saying, this is how does it compare with the FLS scores? So this is basically a classification problem. I used a multivariate statistical method known as linear discriminant analysis to estimate the misclassification error, or the MCE. So the metric that we do is the MCEs. So here is the percentage MCE, and MCE 1, 2, and 2, 1 essentially are about misclassifying one class into class number 2 and vice versa. Of course, the MCE is 0, indicates perfect classification. The results indicate the subject classification is relatively poor, as you can see here, when only the FLS scores are used, but gets substantially better when the measurements from the PFC are used. When the PFC alone is used, the misclassification errors go down to about 21 to 23%. And then, of course, as we increase the number of areas in the brain, we see a sharp decline in the misclassification error, and the least MC is obtained when we use all 3 areas of the brain, and it goes down to about 4.2 to 4.4%. Then we have performed leave one out cross-validation to show that the classification model is robust, and 100% of the samples in the LOCV model have MCE less than 5%. So that answers the 2 questions that we raised. Of course, not every question is addressed here under surgical skill certification. There's still a long way to go, but that does answer the 2 questions that we asked. We move on to the next question of skill learning and transfer. We performed a learning curve study. We recruited 12 medical school students at the University of Buffalo, and who had not been exposed to the FLS before, and divided them into 3 groups. So as you can see here, this is the study design. Gray is the group that trained on the FLS box. The purple group is the one that trained on the virtual reality simulator. And there's a control group here that did not train at all. So they just did the pre-test and the post-test. So each student in the simulation group performed multiple trials a day for 11 days. And each individual in the training groups performed more than 85 trials over that 11 days. And as you can see here, this is a clear learning curve that we obtain as a result of learning. So after training, each group was instructed to wait 2 weeks without any training. After that, each individual has performed 3 FLS and 3 VBLAST trials to test skill retention. So this is about 2 weeks after that. So this is the post-test we're going to be referring to. So as you can see from here, there is no significant difference on day 1. But during the post-test, there's significant difference between the FLS and the VBLAST, the training groups and the control group. And following the retention test, we asked each individual to perform a task on excised cadaveric peritoneal tissue. And the measure was, the measurement and assessment was done by surgeons, as is done in the operating room. So now what happens to the average hemoglobin concentration over the training period, right? So here, what we show for each plot, for each of the 3 brain regions, we have these plots. To the left of these plots, at least to my left, we show what happens on day 1, the first day of training. And then on the right-hand side of the plots, we show what happens at the retention test. That is after the 2 weeks. Orange indicates untrained control students. The black boxes indicate trained FLS students. So as you can see here, on the first day of training, there is no significant difference between the control and the FLS training groups. And that is captured in all the 3 brain regions. Now the retention test, so this is this part of these plots. It is clear that the trained students have lower PFC activation and heightened M1 and SMA activation than the control group. Now we go a little bit more granular at seeing what is really happening during the training process. So we divide the trainees, the 7 trainees that we have, into 2 groups based on the CeMSIM scores. So we can actually plot the CeMSIM scores. 3 of them were unable to reach expert level performance, even after training, and they're labeled as unskilled trainees. 4 reach expertise and are labeled as skilled trainees. So here we show the misclassification errors. So each box is divided in 2 parts, MC1, 2, and 2, 1, where y-axis is the pretest. On the x-axis, actually, we show what is happening to the 3 groups on the odd number of days of training, day 3, 5, 7, and 9. What is very interesting is that we notice that at the very beginning, at the onset of training, there's very poor classification between the groups, as it should be, because they're almost close to each other. But that classification accuracy grows very significantly towards the latter half. Actually, we see a transition almost on day 7. And at the end, we see there's a good classification of skill trained students between the onset and the final. Remember, everything is being compared to the pretest. And there's a good classification between skilled and unskilled trainees. What about transfer? Transfer is a very different beast because, yes, the students have been trained on a simulator, they're familiar with the environment, but now they're asked to do a surgical dissection task on an ex vivo human peritoneal tissue. So both groups, that is the simulator group that they've been trained and the control group that has not been trained, are actually actively strategizing. So there's no significant difference in the PFC. Even after all this training, they're still actively strategizing. But what we see is that for the trained student, there's significantly higher left M1, left medial M1 and SMA activation. And so this study has been performed and published in surgical endoscopy in 2019. Here we show the same misclassification errors and how the error drops significantly from using time alone, which is used in a lot of surgical procedures, time and error, as I said, to around 2%, for example, for the FLS trained subjects when using the 3 parts of the brain, and to about 8.9 to 9.1% for the VBLAST, the virtual reality trainer. And here we show the leave one out cross-validation that was performed to test the robustness of the classification model. So this is our 2 minutes of fame. This work drew a lot of media attention and was published in the Wall Street Journal. So what did we learn from these studies? We saw that FNES metrics can objectively differentiate and classify varying degrees of surgical motor skills. Subject misclassification errors for classifying surgical experts and novices reduced significantly from about 60% to about 4% or so when compared to the FLS metrics. And FNES metrics can also successfully classify skilled and unskilled trainees post-training. But still, FLS is the gold standard, as I mentioned, and it's very hard to displace. Because FLS course is central to board certification and has been adopted by the American Board of Surgery, with more than 15,000 tests administered so far, and a plan to go to 2,000 tests per year. But the computing the FLS course is time and resource intensive, and it cannot be used for providing feedback and adaptive training. So how about we actually predict the FLS scores from brain imaging data? So this goes to a third question of predicting, and that uses machine learning algorithms as well as deep learning. I'm going to go quickly over this. This is quite a bit of work that has been done. I'm not going to go into too much of the technical details. So we look at 13 medical students undergoing learning curve exercise. By now, you have seen quite a few of those. So you're familiar with the paradigm. We have a pre-test to look at the baseline. We have learning, and then we have retention test, and then a transfer test. So for the ease of use and implementation, we are looking at the data only from the PFC. So 6 locations in the PFC directly. And we extracted 7 features from the time series of the FNES data for HBO and 7 for the HBR, so oxygenated and deoxygenated hemoglobin, for a total of 14 data features from the 6 regions. To predict the FLS scores from the FNES data, we looked at several machine learning algorithms like random forest, Carnell partial least squares, support vector machines. And we also looked at a deep neural network, which we call the BrainNet. Actually, Professor Xavier Intas is the driver behind this. He's the co-director of our center. It is quite a simple network. It has 2 convolutional layers connected by 2 fully connected layers. And the model was trained using 30 rounds of 10-fold cross-validation, as you can see here. Then we examined the effect of multiple things on our model prediction using these machine learning and deep learning models. For example, what is the effect of sample size? And the metric we use here is the R-square values. So in this study, we had 13 medical students who collected about 100 raw data points. But of that, we took out quite a few of the data points. We had to because of artifacts in the data. So we used about 702 data points. Now, what happens if I choose a subset of the data at random, right? And I go from 702 all the way to 300 and look at the R-square values of prediction. As you can see here, for a data size less than 600, machine learning algorithms beat the deep learning model. But beyond 600, the deep learning model starts to become better, as is expected. Then we examined the effect of backward feature selection. So we removed one component So we asked the question of what happens if we remove one feature from all the PFC locations or all features of one PFC location. So that is what is shown as the matrix here. So these are all the features for HBO. These are the features for HBR. And these are the 6, so these are the 14 features and the 6 regions of the PFC that we measured. So what happens if we remove one region completely or one of the features at a time? What we found that even if we remove one region or if we remove one of the features, we get a lower R-square value. So the conclusion from this is that best R-square obtained with 7 features of the 2 regions. But removing the HBR slope and the left middle PFC region produces the lowest R-square value. Next, we examine whether the model is robust to new participants. To test that, we further use the leave one user out cross-validation scheme, in which we train the model on other participants' data except one participant and test it then on the participant that was left out, and do that for every participant in the study. So in this leave one out cross-validation scheme, we saw that the brain net, which is the deep neural network, actually does not go down significantly in accuracy, where the other models, the machine learning models, actually do. To further test what happens if we apply the model that we developed to absolute and new participants, right? So we did the study with 6 new participants. Here we show the results for the new participants, the true FLS scores, and the predicted scores. So we see the absolute error in the predicted score is 18 here. This is not very large compared, given the fact that the FLS scores for pattern cutting goes from 0 to 300. So we showed that the BrainNet is robust when applied to a new cohort of participants. So in this plot, we show the predicted FLS scores and the true FLS scores for the machine learning algorithms as well as the BrainNet. Of course, we see the best results are coming out of BrainNet. These green lines, the green dashed outer lines, represent the threshold for passing the FLS. So because we're looking for certification, we needed to delve deeper into that. It's not sufficient for us to just show good accuracy, but show that actually this can be used for certification. So what we did, we decided to look at the ROC curves and the area under the curve, the AUC. So of course, our AUC value above 0.9 indicates excellent classification ability. So we look at the different classification accuracies. The BrainNet provides an accurate AUC of 0.91, followed very closely by KPLS, the kernel partial least squares method of 0.91, 0.90, and the SVR. So it demonstrates good prediction accuracy, of course, with the limited data set we have. So this is one of the major limitations. But the BrainNet, remember, is highly computationally efficient compared to the other approaches, because once the model is built, it can be used with lightning speed. So I pointed out the limitations of the study that included features that needed to be extracted. Of course, because if we took the entire time series data, it is very expensive to build. And of course, we don't have sufficient data to use the entire time series data. We tried doing that, accuracy goes down significantly. So the major problem with that is that we actually have to have larger sample sizes. But this is the first step towards real-time neurofeedback for surgical training, where we can actually use real-time data from a trainee, as I pointed out, in the VIP model. Going back to the VIP model, we can have a learner model, which actually looks at the brain imaging data and can predict at which point in the learning curve the trainee is at, and then provide feedback based upon that stage through the VIP model. So this part of the study was performed as a team. So I mentioned Professor Intes, but also 2 other professors worked with us, Professor Huve Kruger and Pinkung Yang from our biomedical engineering department. Clinical collaborators are Professor Steve Schweitzberg and Dr. Laura Kvodo from the University of Buffalo, Dr. Denise G from the Mass General Hospital, and Dr. Clarice Cooper is also from the University of Buffalo. For the FNES work, we collaborated heavily with Dr. David Boas and Miriam Yusel, as I pointed out earlier, at Boston University. Dr. Arun Namani was a graduate student who did most of the work. And the majority of the work that I talked about was performed a few years ago by Dr. Namani before he graduated, and continued by Yonyan Gao, who just defended this earlier this month. And she's worked on the extension of this work with neuromodulation, which I'm not going to be talking about today. And we thank Dr. Buzz DiMartino and his team at TechN and the support of the NVIDIA Corporation with the donation of the Titan XP GPU and the Quadruf P6000. Quite a few groups were involved in this project. So I'm very close to the end of this talk. So what next? Of course, collect more data. I cannot be more emphatic that we need to come together as a community and collect and publish freely available data sets so that people can work on that and build stronger model. We know that the model, we have shown that the model accuracy increases significantly. We have to show better classification accuracy. We have to be able to use the entire time series data to get features. We are sort of extracting features, which is not the right thing to do because there might be beautiful feature sets that we're really missing. So we are artificially creating these feature sets. Now I talked about the VIP model. I've talked about it multiple times, but that is the grand vision that we have. So we have to generalize the BrainNet to include multimodal data, so data from other sensors, for example, to create the VIP. And the third extension of the work is neuromodulation, being able to use transcranial electric stimulation, work that we have already performed at University of Buffalo, shows very interesting, promising results, but we have to follow through on that and use that with neuroimaging. So we have done those work with neuroimaging, but with not real-time feedback through neuroimaging. So real-time feedback through neuroimaging, I think, has tremendous potential in adaptive education and surgical training. So with that, I thank you all for listening and your patience. So I'll hand it over to Dr. Larry for our questions.
So nice, Dr. Dey, that you have given your time and you have accepted our invitation. And it's really nice to have you. Hopefully we will get back you once again in some other webinars based on your convenience. And
it's all my pleasure. Thank you so much for the kind invitation. And all of you stay well and stay safe.
Thank you. Same to you.